So we're going to start with part A, and the first question is asking us that if we have a linear transformation from V to W, where V and W are finite dimensional vector spaces. If T is injective, what can we say about the nullity of T? And if T is injective, what this means is it means that T of, or if T of X equals T of Y, then X equals Y. And we said that this is true if and only if the kernel of T is equal to the zero vector, or the set containing the zero. Well, the dimension of this space of the kernel, which is the nullity, would be zero. Okay. How else could we ask questions like this? We could ask, what would be the bound on the dimension of W? And then your dimension of W has to be less than or equal to your dimension of V. And there's a whole bunch of relations that we discussed that we'd have to go through and analyze carefully. So these types of questions can be asked in a variety of ways, where we're given some information and using that bounds the dimension of some aspect of the function. Now we're given what is the dimension of our set of linear transformations from R3 to P4. One way to think of this is to create a matrix where the number of inputs is your number of columns and the number of outputs is your number of rows. Here, R3 has dimension 3. Polynomial is a degree at most 3 has dimension 4. So it'd be 1, 2, 3. 1, 2, 3, 4. So it's a 3 by 4 matrix, or a 4 by 3 matrix. When we multiply this, we get 12. Next, we have a 3 by 3 matrix, and we're looking at the dimension of W. Again, what this is the dimension of the output. And every vector, if you look at T, V represented in beta, every one of these vectors is one of the basis vectors when you apply T to it represented in beta. So the number of rows is the dimension of W. So here we have 3 rows, so our dimension is 3. Now, here, this is an interesting true or false question. If we have a linear, or if we have a function mapping V to W, and the 0 does not get mapped to 0, then T is not a linear transformation. What we need to do is we need to just verify for ourselves that T of 0 does not actually equal 0. And this is true. This transformation, because T of 0 doesn't equal 0, one of our results of being a linear transformation is that T of 0 would equal 0. So this would mean that T cannot be a linear transformation. Now we have a linear transformation going from the 3 by 3 matrix, or the 2 by 3 matrices to R3. And it's said that it's surjective, which means that the image of T is equal to R3, or the dimension, the rank of T is equal to 3. Now, using rank nullity, rank of T plus nullity of T is equal to the dimension of V. So 3 plus the nullity of T equals, and here it's the set of 3 by 2, and it should be real matrices, has dimension 6. So here the nullity is going to be 3. A6 is a really interesting question because the dimension of the n by k real matrices is n times k. And we're saying when does this equal n plus k? And there's actually two situations, but one we're going to talk about. And if we do 2 times 2 equals 2 plus 2, this is verified. This is true if we're multiplying by, if we have two, both n and k are 2. But this is the big setup, is that what two numbers do you multiply and add and get the same result? For A7, if we have a linear transformation T, the function can be understood by knowing what it does to a basis. This is true. If we define T by what it does to a set of basis vectors, and we know it, and it's a linear transformation, it's completely understood by what it does to a set of basis vectors. In fact, this is how we create the matrix representation of a linear transformation. So in A8, we have a linear transformation going from C2 to C3 such that this is our function, and we're asking, is it surjective? Well, in order for it to be surjective, the dimension of the image of T must equal 3. But with our rank nullity theorem, this has to equal 2 because that's the dimension of V, which means that the rank is less than or equal to 2. So the rank does not equal 3. So this is no. We can't be surjective just by our dimension bound. Now, A9, we want to provide a basis for R3. Here we can just provide the standard basis. And here, if TS is linear, then both S and T are linear, and this is false. And we can have a counterexample that contradicts this, and we have S equals x cubed, T equals cubed root x, TS equals x. TS is a linear function, or sorry, S of x, T of x, TS of x. TS of x is a linear function, but S of x and T of x are both not linear functions.